This is Chrisferb, and I'm going to review example 3 of the Poisson distribution probability examples. So the setup for all of these is the same. You'll notice if you've seen the example 1 and 2. A book publishing company has determined historically its books have 1.5 errors per 100 pages of print. What is the probability of having 5 or fewer errors in 400 pages? So that's the big difference here, is we actually have a range, 5 or fewer, and then 400 pages. So in example 2, we had 400 pages, so that wasn't a big deal. We increased the t value, or the time parameter, to 4, which took care of that change in the interval we're looking for. So in this case, we're still looking in the 400 pages, so 4 times the interval that our lambda is in, except we're looking for 5 or fewer, so a range. We're looking for 0, 1, 2, 3, 4, 5. So that's a little bit of an issue for us, although it's very solvable. So here we go. There's a lot of writing in this one. So 5 or fewer. So let's write out what we know, which we always do first, what we know. So lambda is 1.5. And as I mentioned in the other 2 videos, if you haven't seen the Poisson example 1 and 2, go take a look at those. I use what's called a Poisson parameter, which is just mu, which is just an average. But it's an average that's based with, it's based on the time range, or the time interval that we're working with. Okay, so this is our lambda, and that's the symbol for the lambda. And then this one, our t is going to be 4, which is very similar to our last problem. And then our e is the constant, and it's always 2.7182. I usually go out 4. That makes it accurate. It's more accurate on your calculator because it'll go out further. I think it goes out to 8 or 10 decimal places. And then this is where the rub is. We're looking for our x, we're looking for equal to or less than 5 errors. So when we go and multiply out 4 times our lambda value, 1.5, we end up with our mu, which is 6. And that's because that's when you take the lambda times the t, we end up with mu, which I've been doing essentially the calculation in our head for example 1 and 2. Okay, so I'm going to draw out for this example, and this is kind of the basic setup, just as a refresher. We end up with mu, e, and we end up with x up here, and then to the negative exponent of mu, and then x to the factorial. Okay, so that's the basic setup. But to do this type of question, we actually have to do this. We have to have P0, P1, P2, P3, make sure I'm not going off the screen here, P4, and P5. So it gets a little bit cumbersome, you'll see. And it's okay, we can deal with it. I'll show you how to do this in the calculator. It's a little bit different than the first example where I showed you on the calculator. So I'm just, to be efficient here, I'm going to fill these in, all the parts, so that okay. So for the top, let's see, for 0, it is still 6, 0, and 2.7182, 6. So all of them have 6 parentheses, we all have 2.7 182, 2.7182, 2.7182, 2.7, oh, 712, 2.7182. I'm guessing you're getting the point here. Okay, so the first one was 0, and then 1, 2, 3, 4, 5. And the negative exponent is 6. Realistically, I'll show you how to do this to make it a lot easier, and I'll later show you how to do this in Excel. So our answer when we calculate these all out, I'm just trying to make it make sense to you, at least in your head. So the first one's 0.00247, which is one of the answers that we already calculated. And then 0.0148. And then 0.0446. And then 0.0892. And then 0.1338. And then 0.1338. That's interesting. We'll have to make sure that we're correct on that. Okay. I kind of think that's a typo, but we'll have to figure that out. Okay. So when we add these all up, we end up getting our answer. I'm guessing this might be both of these the same, might be an error, but our answer ends up being, I know the answer is right because I'll pull it up on the calculator. So 4457. So that's what our answer ends up being, 0.4457, or about 44.57%. So now let's take a look at the calculator. So in the calculator, what we do is we do the same type of setup as we did before with our Poisson PDF, except we do second distr, but this time we're going down to the PoissonCDF, and that's the cumulative function, probability function, or density function is what they call it. So in this case, it's the same type of values that we're putting in. So we put in the value for our mu right here. And that value for our mu is 6, okay? So the value for our mu is 6. And then we're actually looking for on this one 5 or, so our answer is 5 or less. So we're going to put in 5. And then hit enter, and then we hit enter, and we end up getting the same answer, 0.4457. And actually the calculator said 0.4456, so that's okay. We must have rounded. Okay, so that's how you do this on the calculator. It makes a lot of sense to do it on the calculator versus going and doing each part. So this is when we have a PoissonCDF. So we're looking for a range within the data that we're looking for. Instead of it being an exact probability density function, we're looking for the cumulative density function. And that's when we use the PoissonCDF function. Thank you.